In this video, we will discuss about the viscous flow in a pipe. So this is a tube in which the fluid is flowing. So the fluid flows in a pipe. When the fluid flows in the pipe, the bottom layer of the fluid, there's a molecules here, will get stuck to the pipe due to viscosity. And as you move up, so if you draw a cross section here, as you move up, the velocity increases. So in the middle, the velocity will be maximum. So the velocity profile will be like this. We need to find out what is the velocity in the middle and also other locations. For this, so this is the side view of the pipe. For this, we will consider a fluid element. So the fluid element's dimension is, so the radius of the pipe is capital R, and this fluid element is a distance of y from the pipe wall, and also the radius of this cylindrical fluid element is small r. You can see that here. On the left side of the fluid element, we have a pressure force which is equal to the pressure here into pi r square, that is the cross-sectional area of the cylindrical element. On the right side, you have a pressure force which is equal to P plus dou P by dou x into delta x into pi r square. This dou P by dou x into delta x is the change in pressure as you go towards right. So into pi r square will give you the pressure force. And the length of the fluid element is delta x. And you have a friction force acting on the surface of the fluid element, that is tau into 2 pi r into delta x. This 2 pi r into delta x is the surface area of the fluid element, 2 pi r being the circumference of the cylinder, into delta x will give you the surface area, and tau is the shear stress acting. And here, if you do a force balance, here we are assuming that the fluid is not accelerating, so that it is a fully developed fluid flow. That means the total force acting in the x direction will be 0. So the forces acting here are pressure force and viscous force. Gravitational force is neglected. It is in the y direction. We are taking only in the x direction. So P into pi r square minus P plus dP by dx into delta x into pi r square minus tau into 2 pi r into delta x is equal to 0. Here dou P by dou x can be written as dP by dx because pressure is a function of x only here. It depends only on one variable. So the partial differentiation can be converted into full differentiation, that is dP by dx. So on simplifying this equation, you will get minus dP by dx into small r by 2 is equal to tau. So you can cancel off this pi here, and p gets subtracted, and this r will be reduced. Here it will become 1, and delta x also will get cancelled off. So you will get minus dP by dx into r by 2 is equal to tau. And so tau max is equal to the shear stress, maximum shear stress is equal to minus dP by dx into capital R by 2. This is the maximum shear stress. So if you draw this pipe and take a cross section, so shear stress will be 0 in the middle and it goes on increasing. So shear stress at the wall will be maximum and at the center shear stress will be 0. So this is according to this formula, minus dP by dx into r by 2. When small r becomes 0, shear stress becomes 0. When small r becomes capital R, shear stress will be tau is equal to tau max. And you know tau is equal to mu into du by dy. Actually, this is Newton's law of viscosity. We need to convert this equation in terms of small r. You know y is equal to capital R minus small r. Okay, this is the uh, radius of the pipe. You can see this in the figure. Small r is the radius of the cylindrical element, capital R is the total radius, and y is the distance from the pipe wall. So small y is equal to capital R minus small r. So tau is equal to mu into du by dy. And if you convert this tau is equal to minus mu into du by dr. Because since y is equal to capital R minus small r, you can write dy is equal to dr minus d small r. This is a constant, so this will become 0. So dy will become minus dr. So you can write minus mu into du by dr. If you substitute this tau here, you will get minus dp by dx into r by 2 is equal to mu into du by dy is equal to minus mu into du by dr. From this, if you solve, you will get, if you rearrange this equation, you will get du is equal to 1 by 2 mu dp by dx into r into dr. So this dr will be taken to the top, r into dr. So, and then if we integrate, you will get integral du is equal to integral 1 by 2 mu dp by dx into r into dr. And on integrating, you will get u is equal to 1 by 4 mu dp by dx into r square plus capital C. In order to find this constant, we need to apply a boundary condition. This boundary condition is that the velocity at the wall is 0. When there is a fluid flow, the molecules will get stuck to the side of the wall. Here the velocity will be 0. In the middle, you will have maximum velocity. So you know the velocity at the boundary. That is a boundary condition. That means u at capital R is equal to 0. That is at the wall. So if that is equal to 0, you will, if you solve that, you will get C is equal to minus 1 by 4 mu r square into dp by dx. And so u is equal to minus 1 by 4 mu dp by dx into capital R square minus r square. When you substitute this constant C into the equation, you will get this formula. So this is the velocity at any position, at any radius r. So u max is equal to u center, that is equal to minus 1 by 4 mu dp by dx into capital R square. So u center means velocity at the center, that is small r is equal to 0. So this is equal to minus 1 by 4 mu dp by dx into capital R square. So this is the velocity at the center. And if you try to plot the velocity, so for a pipe here, if you are trying to plot the velocity using this equation, you will get a parabolic profile. That means the velocity will be maximum at the center, and also the shear stress will be like this. Shear stress will be 0 at the center, it will be maximum at the wall. And if you take any, if you take any cross section, the velocity at the middle will be maximum, at the center it will be 0, and you will have a parabolic profile. Here shear stress is linear, so towards wall it will increase.